Set it down so it just. It's going to take 15 minutes. Hang on.
Sorry, guys. So I'll just move back so you can ask me for a desk. Would that be easier?
I mean, if you don't mind actually being here, no, you can stay here. Just, we will stay here. Okay.
So this is group E. D, yeah. Surface finish.
Okay. Yeah. So good afternoon everyone. We are the group A, and today we're going to present surface finishing techniques on FDM parts. Attending TCT show helped us to choose the topic for this project, as we became very interested in the process of surface finishing of 3D printed parts. This led us to do further research in this area, and we discovered a number of surface finishing techniques, such as abrasive jet blasting, mass finishing, electroplating, bead blasting, vapor smoothing, and a few others. Fundamentally, 3D printing is a material layering process. However, today, to stay in nowadays competitive market, it's very important to achieve high quality to meet aesthetic requirements and functional properties. So the aim of this project is to reduce surface roughness by introducing an after-treatment process. Surface roughness can be reduced by either removing the material, thus reducing the steps, or by adding a material, thus creating a new surface covering, with a smoother covering.
So I investigated mass finishing. Mass finishing is pretty much where you have the part and you have it surrounded by an abrasive media. The media can come in different sizes and different materials. You can get it in, mainly comes in ceramics and plastics. Traditionally in the past it's been using metal parts, this process. However, companies like Stratus are now applying it to FDM parts. So as an example, there before and after treatment. As you can see, in the end, you can get rid of most of these steps and can reach the more intricate areas. That's assuming you use the right media. And the three techniques that you have within mass finishing is your vibratory finishing, your tumble finishing, and your essentially your bow finishing.
So I investigated vapor smoothing. Vapor smoothing essentially consists of having a solvent liquid, usually for FDM parts that liquid is acetone, and you raise it to its boiling point, which produces vapors of the solvent. These vapors come into contact with the part and melt away a tiny layer, so you get rid of your steps and you're left with a smooth, shiny surface. The main downside to the process is the fact that you're boiling acetone, which is quite dangerous. So that's the main downside of that.
I looked into abrasive flow machining. It's basically two piston chambers that have a certain type of media inside with an abrasive grain. The chambers have the pistons move up and down where the part is fixed in the middle. As the media goes up and down, the part gets polished. And this is very advantageous for polishing internal passages, such as pipes and all that. It's very suitable for polishing surfaces that involve contact with a fluid, like turbines, propellers, and as I said, pipes. It can generate very smooth surfaces. The RA can be down to 15 nanometers, which is very high, relatively low. And disadvantages is that this process is actually very costly. To build the machine, there's a lot of material to be needed, the pistons and everything, and especially the media can be very expensive as well. And it's a relatively slow process. And for most applications, it's not really used for polymers. It's usually used for metals with very high pressures. So that's it.
I looked at the electroplating process, which is the process of depositing a thin metallic layer onto the workpiece. Traditionally this is just done on metallic products, but recently new conductive coverings have come out so that polymer parts can be covered as well. The basic process is the parts are put into a chemical bath and current is applied across the circuit, and the metal ions move from the metal block to the workpiece. The major benefit of this is that 3D printed parts can be covered in a metallic surface, so they appear to be final finished product without the cost of machining. However, as the metal encases the full part, if the internal structure expands, then cracking can occur on the surface.
Abrasive jet blasting can be described as a process of removing the contaminants or finishing of the surface by streaming the abrasive media directly on the surface of the product. As we can see, you can subdivide the process mainly into wet and dry blasting. The main differences are illustrated in the pictures. So A and B illustrates dry blasting, and we can see 90-degree ricochet occurring, which provides high abrasive rates, whereas wet blasting achieves reduced ricochet angle due to the cushion effect provided by the liquid. Depending on the media, abrasive jet blasting usually leaves a matte finish, and it's widely applied in many industries to deliver aesthetic and functional properties.
So after researching all those technologies, we had to decide which one we wanted to progress to the next stage. We put together these factors that we might want to consider, like time and safety, how easy it would be to build it, and we ranked those based on how important they were. In the end, it turned out that paper spoon was the best option. It scored quite well in all of the categories except from the safety. However, the safety concern was too significant of our last one, so we decided not to go with that one in the end. We just bought the matte finishing, which still scored quite well. The only one where it was quite poor was the timing, which was got a score of 1. It takes about 5 or so hours to do the treatment, which was quite poor when you compare it to paper spoon, which takes less than a minute. So after choosing matte finishing, we had 3 to choose from within there. So you had the vibratory finishing, the tumble finishing, and the centrifugal barrel finishing. We felt that vibratory finishing was the best option to use in terms of getting the internal areas of the parts. The other two methods don't necessarily compare that well when looking at vibration finishing. So after choosing that, we put together 2 initial concepts. One was just to simply have it hanging from something with the motor spinning underneath with an eccentric weight. This would give it a vibration. The second concept was quite similar, but to put on springs. So we had this motor underneath as well, which was spinning with the eccentric weight. We felt a bit more comfortable with concept 2 in terms of further developing it, with doing the calculations of the springs and the FE analysis, so in the end we did both concept 2.
So after choosing to go concept 2, this was the initial CAD drawing we came up with. As you can see, it's quite a bit different to the actual finished product. It involved nuts and bolts to secure the springs in the right positions. And also, as you can see, the boards were quite big, so there's quite a lot of wastage, which, as you'll see in a few slides' time after the FEA, we managed to cut quite a lot of that out.
We did an FEA analysis on the final design. We set the top platform to be the weight of the entire system, and then we let the FEA do its thing. So we found out that the natural frequency of the system was about 48 Hertz, which was necessary to know whether the motor that we had inside was strong enough, because it's only 10 watts, whether it's good enough to provide resonance for the system, and also we needed this data for the calculations in the following graph. We used this graph to do all the calculations. This is the vibration formula that uses damping ratio and other factors such as the extrinsic mass, damping ratio and the mass of the top, right? So to find the stiffness equivalent stiffness constant, we move the slider and let the frequency, resonant frequency, to be the same as on the FEA. This way we had almost all the factors except for the damping ratio, which we initially set for 0. but the next slide, and now we run the machine to see what is the amplitude of the resonant frequency, and we found out that was about this, and then we moved the slider to match the actual physical experiment amplitude with the graph. So this way we could actually find the damping ratio. And with this graph, we could actually then use these results for further results for testing. So for example, if we chose one frequency, we would also know the amplitude at that frequency, and we would know the frequency times the amplitude would have an effect on the polishing time of the part. So this graph was very important for obtaining different results.
Okay, so once the FEA analysis and all the spring analysis and vibrations have been done, this was the final validated concept that we came up with. It includes hollow cone, copper instead of a cone, so the motor could be fitted inside. The motor is then encased into 3D printed specific shapes there, and that sits on a much smaller platform. And instead of the nuts and bolts, we've now got 3D printed pegs on all sides, which cut costs and weight. It also includes a new safety guard to prevent the spinning mass from injury anyone if it came loose. So the nuts and bolts were replaced with the 3D printed pegs. This also ensured a tight fit, as we could specifically design them for the springs we had. Also, as there's no permanent fixings, it means that different springs can be replaced very easily. So this means that if we find that we need to change the media, which makes it much lighter, then we can change the spring constant to get the correct vibrations. As the motor is held inside the cup, it also means that reduces the dead zone in the bowl as the media rotates around the cup. And finally, as the motor is held in place with this specifically designed 3D printed case, it reduces any movement that's caused vibrations, so it should mean that the motor nothing comes loose inside the motor when it's vibrating.
Here we've got cost comparison between our initial and final design. So if you investigate, the tables don't include the media, just because the media must be deliberately selected for certain application. So initially what we found that the price of the product itself is exceeding our budget, so we had to look for alternative components and manufacturing processes. What we did is we conducted a FEA analysis, and we found that the length of the springs has a negligible effect on the machining performance. So instead of buying initial springs, we got the shorter ones with the same stiffness value, and thus we saved £19 on the springs. Furthermore, instead of buying fixings, we 3D printed the pegs, and that saved us £12.50. Overall, the final design price was reduced by £31.
So then we moved on to the manufacturing process. So we used MakerBot to 3D print the custom parts we've designed, and we also laser cut the MDF boards, as we thought that would minimise human error when positioning the holes to get the part accurate for the springs to be in the right places to match the FEA analysis. So once we've manufactured all those pieces, we moved on to the assembly process. The entire machine only fits together with just 4 fasteners, which we thought was a very good design for assembly feature, because it's quick to assemble. And it only took about 15 minutes to manufacture the entire machine, which again is a good design for its feature.
So in the end, this is what we ended up with. As you can see, it matched pretty much what we expected from the final CAD, the physical model. One minor change is that we had the assistance from Dave in the workshop to have a weight that we could adjust, so we can slide it to the left or fill it into the axis of rotation, which allows you to have control over the amplitude of the system. Just go to the next slide. We have a video here of just when we're doing the tests. I think someone's running at half the speed with the weight at its furthest point. I can see that, and then that causes the deflection in the springs as well as it rotates around.
Testing validation process including testing two types of hollow specimens, the prism and the cone, at 5 different positions as indicated in the image. To examine the effectiveness of the machine, alicorn microscope was used to generate a 3D scan of the specimen, and it allows to measure the roughness to the fraction of the micron precision. Surface roughness was measured. Surface roughness is measured after different time intervals, thus achieving the optimum time required to achieve the desired roughness, and at different positions, thus achieving the effectiveness of the vibratory machine on different profiles and different complexity parts. However, after 18 minutes of running the test, our motor overheated, and we didn't achieve the results that we desired. And what we found that after 18 minutes of running the machine, the surface roughness was reduced by 11 microns, thus led us estimating that the longer running time would actually achieve reduced roughness. So that's what the project was aiming for.
Okay, so obviously, as it wasn't a complete success, there are some improvements that we need to discuss. The major flaw in this was the component failure of the motor, which couldn't handle the prolonged time when it was on. So to improve that, we'd have to get a motor which is more specifically manufactured for long running time and has a better cooling system. This would be quite an easy change to make to a machine, as the motor casing can be specifically 3D printed and then slide back into the casing without any other changes. To further develop this, also we would like to change the design slightly to allow lubrication to be added to the media, so then different components and different medias can be used. To do this, we'll need to remove the holes which are in the bottom of the machine at the minute, which will stop the lubrication from staying in. And finally, we'd like to improve the assembly process by pre-creating the holes where the fixings go into, as this was done by hand originally, and it meant that they could only be fixed in a certain position, as there's a slight human error from that.
So, any questions?
Okay, thank you very much, guys. Any questions at all on this?
Did you find out why the motor overheated? Do you reckon it's because it's got so much casing around it?
Yeah, well, it just couldn't carry the load for such a long time as we expected, and it wasn't powerful enough.
It was only 10 watts.
Yeah, and the load was quite high.
We think by applying the weight as well may have caused that problem as well.
Where does the motor come from?
Where did the motor come from? Yeah. It was like a buffer, spinning buffer.
For nails.
Like a Dremel sort of thing.
Yeah, which is, you wouldn't expect it to put for nails,
We were planning on giving it a break, say every half an hour, and then turning it off, but obviously it failed before that, wasn't it? We were able to do that, so.
Basically, we chose the motor just because we can adjust the speed, thus controlling the abrasiveness, and it looked very convenient. It just didn't last as long as we expected. Yes, please.
What's the current media that you have inside the motor?
This is ceramic.
Yeah, the media is plastic. It's about 12 millimeters in height. So that was quite the smallest we could get. It's quite expensive media, and the smaller you get, the more expensive it gets.
Yeah.
The cost of that media came to about £10 per kilogram.
Is there any particular reason why you used that?
It was based on price and convenience, but also the portable shape is quite effective compared to other ones.
Yeah, and the costings that he's produced to see how much you saved, did you look at how much the extra motor, the additional motor you would need would change the pricing?
We've not known, because the costings was between the initial design and the final design, which both use the same motor. We only had the motor issue towards the end of the project.
Is the motor guard on the bottom attached to both wooden boards?
No,
No, it's just to the bottom.
Right.
It's top one.
Oh,
bottom.
Sorry.
Is the roughness, like when you're sanding it down, is it not done more from the medium rather than the vibration? Or
it's the vibration that causes the aberration, because you can imagine as the beads move inside, they kind of hit against the parts. That causes the vibration. But that is the media that causes the aberration. But the differences in the frequencies and the amplitude have an effect on how much abrasion takes place.
Thank you very much, guys, for taking that on, because it was a bit of an unusual project for you to take this one on at all, or to come up with. What stops the bowl from abrading away? Your plastic bowl on the outside? Time. So you got that's a reusable, that's a disposable.
Oh yeah, it's a very cheap part of the project.
It's like £3 anyways.
If there was any sign of that, I'm sure you could replace it very quickly.
Yeah, but because it's so easy to take apart, that bowl would be really easy to swap. So if that did occur, you could swap that bowl out quite easily.
Is it even possible?
Thank you very much, guys. Thank you.